Okay, so we are going to have both Peter Haigh and Ross Halloran, who are members of the micropower management team at Tyndall, will be presenting the tools that the group has developed for predicting, standardizing, and optimizing system-level performance of Power IoT solutions. And as I said, there'll be around 20-25 minutes talks, and when that's finished, we'll have a questions and answer session. Thanks again to all for registering and for attending. I hope you find it interesting. And just a final reminder, if you could please turn off microphones and cameras during the talks, thank you. So I'll pass it to you, Peter.
Yep, sure. Let me just share my screen now. There we go. Okay. Okay. Good afternoon, everybody. My name's Peter Haigh. I work in the ICT for Energy Efficiency Group in Tyndall National Institute. And I'm going to talk a little bit today about some of the tools that we have been working on for predicting, standardizing, and optimizing system level performance of Power IoT solutions. And this is under the entails project. So the talk today, I'm going to start with a sort of an introduction on the whole area, just to give it a background as to why we would even want to sort of develop these sorts of tools, and just to introduce those of you not familiar a little bit about the entails project and how it is in the context of that project. Then I'm going to talk a bit tool itself that we've worked on. Then Ross O'Halloran, who also works in the group, he's going to talk a bit about the work that he's been doing in terms of a battery lifetime calculation testbed. And then at the end, we'll just give you a little bit of information about the virtual access offering and other simulation work in entails. So I suppose, what's the scale of the challenge in IoT? So there's many different sort of references, and essentially it's talking about hundreds of billions of devices and sensors. So a lot of sensors and a lot of growth. So there's a lot of sort of emphasis on focusing in the whole area and trying to optimize the performance of everything. And so some of the key applications: condition monitoring, energy process and efficiency. And so what do we need for this? We need sensors and actuations. They need to be cost effective, and especially in the retrofit case, they're battery powered. And so to extend those battery lifetimes, we sometimes look at energy harvesting, and then trying to integrate all that together for optimum performance is a challenge. And so that's why we're interested in sort of developing tools to be able to do that. So what is the power challenge? So we're trying to prevent this poor little battery over here from dying in that most awful way, as you can see with the green gunge. What we're trying to drive to is these sort of battery-driven deploy and forget sensors. So most suited to retrofit. Replacing batteries is expensive. Okay, so there's a number of costs. There's the most significant one is that you have to pay someone to go and replace those batteries. So in a factory with tens of thousands of sensors, you have to that's quite a big challenge. Yeah, even finding the one that has been done. So that's very expensive. So you need those maintenance schedules. You often means you might have downtime and all this type of stuff. And so being able to extend this life, to outlive the life of the sensor, if you like, is very important. The physical cost of the battery itself, of course, is always important. And also there's environmental costs. The materials that's used to mine this stuff is as an environmental impact, as well as at the other end in disposal. So the challenge is complex and it's costly, and it's important to know how long a battery will last accurately. Okay, and so that will that will help us with all this thing, trying to make the battery last longer, and knowing exactly how long it's going to last will be of great benefit. So some of the challenges that it's focused on enables is this interoperability challenge. And so an energy harvested power system is quite a complex system. As you can see, it's got a few different elements there, and they're all intertwined in some way. So to enable development of these complex systems, the power management and the energy storage and the sensor and that sort of stuff, there's a number of functions that are required. These are all sort of orbiting around our sort of system, if you like. And to be able to effectively design this, what would actually be useful is if there was some sort of standardization of interfaces and models and this type of stuff. It would help to be able to create solutions much faster if you could sort of plug and play these in together. And so there's a number of enablers, yeah, which you can see orbiting around there. There's sort of standardized characterization methods. Okay, so that's a key thing. So we can measure the same parameter but measure it quite differently and sometimes get different results, and so that can be quite confusing. So standardizing how that's done, common simulation tools and interfaces, design methodologies, and having a consistent way of doing this, standardized component of libraries and early collaboration, if you like, in all elements of that. So these are all sort of parts that the Enables project is trying to look at. So the industry challenge, yeah. So how do we make batteries outlive these sensors? So one of the solutions is to bring together academic and industry partners to develop components that can be integrated into optimized systems. So a key enabler is to standardize components, tools, and systems to be able to do that. So what's under the hood of Enables? Okay, so Enables is a project that's trying to address this, yeah. So how does it achieve these goals? So it's trying to build an ecosystem to power the Internet of Things. So you can see down the bottom there, there's a number of entities there which have come together to be able to do this. Some of the leading research institutes in Europe. We're trying to drive system level thinking and optimization, and do that via these collaborations and interoperability and standardization, as I spoke about previously. And then Enables is sort of got two legs, if you like. So one is the Transnational Access Program, and so this gives free of charge access to expertise and laboratories of the research institutes there, which are listed at the bottom. So it's free of charge. It can be feasibility studies, it can be simulation, characterization. It just depends. So to sign up, all you need to do is go to the enablesprojects.eu website. So it's well worth doing. We've done a number of projects under that. And then the other part of the Enables projects to try and sort of solve this problem is the joint research activities, and these are creating sort of system optimized, application orientated solutions. So these are collaborations between these entities that are trying to de-risk this sort of standardization methodology. Okay, so now I'm going to move on to the system level simulation tool that we were working on. So the Recast simulation tool, this is at Tyndall we've been developing sort of system simulation tools, okay, and in Recast what we've done, we've built upon a tool that we developed on previous projects, and specifically it was a project called Robust, to address these challenges, okay. And so the idea behind this particular tool that we were developing is to try and give a simplified in terms of the use, a tool that can be used by component designers to trade off system performance easily. So So, if you're designing a PMIC or you're designing a sensor, to be able to easily see what the impact of your specification might be on a complete energy harvested system. Okay, and also one of the other objective was to try and help system integrators as a validation tool in the development process. So if you can imagine, there is somebody who is trying to implement a wireless sensing system. They want to extend the battery life, and they want to do that by, let's say, adding a PV cell. And so a tool which enables them to sort of do a simulated plug and play to see what that might look like. And so what we've done as part of the Recast project, which is an Horizon 2020 project, which is a project which is all about retrofitting technology to buildings to improve their energy performance. That was a good opportunity to be able to give it a focus, to be able to develop this some more. And this work was done by one of our master students, Kian O'Shea. So the basic blocks of a simulation, are shown here. So you've got the harvester, you've got some means to extract the energy in a power management function. Then you very often need to store the energy, because very often when you harvest energy, it is only it's not reliable, in that it's not always there constantly. So like, the daylight only lasts so many hours, or the thermal generation changes through time. So you need to store that, and then you need to then condition that voltage to be able to power the sensor node. Okay, so the sensor node generally wants a consistent voltage, and so again, you've got the same thing. You need to efficiently transfer the power, if you like, from the energy storage to the sensor node. And so these are the various elements of a system that we would consider. So an important part of the system, of course, is the GUI. So here's a screenshot of the tool that was developed. Okay, and you can see that. Let's turn on a pointer. There we go. Yeah, so you can see that we've got our system here. So we've got our harvester, in this case a solar cell, power management IC, supercapacitor, so just energy storage, DC converter, and our device. Okay, and so this is the initial screen that you would be faced with, so now we're going to talk a little bit more about what happens when you sort of press these buttons, this type of stuff. And so what you can see here is that we have a number of soft keys where you can set these elements up. So just to add a bit more detail, of course, there's many ways that you could implement a energy harvesting system in terms of how it of how the load would take energy either from a battery or from the energy harvester itself. And so I just want to put this little diagram up here just to be clear on how this particular simulation works. So how this simulation works is that the load either takes the power from a primary battery, or it takes the energy from the energy harvested source. And so this is an example of a system which is trying to make that primary battery last longer. And so there are two voltages, which I'll talk about in a bit more detail shortly, whereby you decide whether you're going to power from the energy harvester. Okay, so there's a turn on voltage level, and I'll explain that a bit in a minute. or whether you're going to power from the battery. So of course, you want the switch in this position as much as possible. But that's the fundamental, if you like, behind this particular simulation. There are other ways you could do this, but this is the way that this simulation tool works. Okay, so you remember those soft keys at the top there? Okay, so I just rearranged them a little bit differently here. Let's go here. So now I'm going to walk you through what happens when you select these. Okay. So the first one that you might select is the sensor, this is a very simple model of a sensor. It just averages the power, so it gives you a constant voltage and constant current draw. Yeah? And so you're able to enter that in there. So of course, many wireless sensors, like a BLE sensor, that would have a duty cycle with it. So what you need to do is measure the average current of that device, and then you can put your operating voltage and operating current in there. Then you would set up the energy storage. Okay, and so the energy storage is your supercapacitor and also your primary battery. Okay, so for your supercapacitor, you can put in various parameters. So the capacitance, the equivalent series resistance of the supercapacitor, the leakage current, and then you can turn on. Then you can configure your turn-on voltage. So this is the voltage at which the energy harvester is selected. Okay, and the minimum voltage. So this is the voltage where you'll end up switching to the primary battery. You can't see it here, but if you selected this pull-down menu, you would have a range of batteries like coin cell or AA size batteries, which would be the type that you would select for your primary battery. Then you have your energy harvesting device. So you can select in this tool either a TEG or PV. And so here, this is what happens as you select for a PV. So you can select the type of technology that you want to select, and you can select the size of the cell, and you can input the lux level that you expect. Okay, just last one here. This is a DC to DC converter. So again, the pull down here, you can select some predefined components. So just to finish off on here, you see it in the red here. If you have either an energy harvesting device, a supercapacitor, or DC to DC converter, your own one, which isn't part of these models, what you can do, you can characterize them yourself, and you can store them in a specific directory, and then they'll come up on your pull down menus here, and you can select those. So there's a certain amount of customization that you can do. Okay, let's move on. So now we're going to look a little bit about the simulation output. Okay. Okay. So in the simulation output, you saw on the initial screen is that you have this indicator in the left-hand corner. And what the indicator shows you is that you have the availability of the energy harvesting energy, and you have the energy that's stored in the supercapacitor. So if you actually run this live, what you actually see, for example, if you have a PV cell, it will assume that you're running over a certain amount of time, that for a certain period of time you'll be in sunlight, for a certain period of time the lights will be on, a certain period of time they'll be off. And so this is what you would see. You would see when the lights are on in the office and when the lights are off in the office, shall we say. And then you'll see your supercapacitor energy drop and rise. And then also you'll see these types of plots as well. And so generally speaking, this is probably the more interesting plot for the user. And what this shows you is that for the primary battery you selected, this is the lifetime of that battery on that particular load before the battery expires. This is what this shows here. Okay. So the blue graph here, what this is showing you is that if you implemented the energy harvesting system, this is how long that primary battery would last before it depletes. So let me explain a bit more about this. Also on the output is a plot of the supercapacitor voltage against time. Okay. And so this is very important in the calculation, as what you see is that, again, an assumption of simulation, it's just the way we set it up, is that it assumes that the battery, that the supercapacitor is always fully charged, okay? And so in this particular scenario, you can see that now we get to a point where the supercapacitor is charged, the switch is turned through here, so we power through the energy harvester, and we're now in darkness, and so the sensor is being powered entirely from the supercap, and it's dropping very, 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 very quickly, and eventually it hits this minimum voltage point. Okay, so as soon as it hits this minimum voltage, it says, well, I've lost all my energy in my supercap, I need to switch over to the primary battery now. So it switch over to the primary battery. Okay, so the voltage on the supercap continues to fall a little bit, because actually the supercap has got its own leakage. So even though we're still in darkness and we're being powered from the battery, actually what's happening is that the supercap voltage still falls a little bit because of leakage. Okay, but then eventually the lights turn on, and so we're still powered from the battery, but now the supercap voltage is increasing, because now we've got some light, and the energy harvester, which is a PV cell in this case, is now increasing. And eventually we get to a point where the voltage is fully charged. Excuse me. So once we get to this point here, we find that we now switch back. We now switch back because we've hit the turn on voltage, and now, just because of the way this particular simulation was configured, is that the supercap voltage is remaining stable, because also you're also harvesting energy at the same time, and it just happened to balance out. And then the lights go out, and you can see now the lights are going out. We're not charging the supercap anymore, as well as taking the power away, and now we're just charging again. And so that goes on and on and on. And so you can see, therefore, that because we're not using the battery all the time, we're now extending the battery life. Okay, and if we ran this for long enough, you'd see eventually that the energy in the battery would deplete, and so then that would end the lifetime of the cell. So just a quick look at some other features here is that when you run the tool, it will graphically show you on the GUI when it's being powered from the battery and when it's being powered from the energy harvesting system. It just makes it a bit clearer, so you don't have to spend so much time trying to interpret the graphs there. So the energy harvester, it's if we look at the PV cell, it takes some pre-measured IV and PV curves that we have built in. But as I say, you can also do your own characterization and enter that into the tool. And then for the energy storage, we also have this all pre-configured. And so obviously the energy storage is powering the device from the capacitor. The DC to DC converter is a very simple model. It is just a simple characterization at a particular voltage level of the efficiency of the DC to DC converter, and so that's included in the model as a power loss. So just a quick sort of look on a little bit of work that we did to
Yep, cheers, Pete.
You should be able to, hopefully.
Just a sec. Yep, can you see that?
Yeah, I can see your screen.
Yep, perfect. Okay. So, hi guys, my name is Ross O'Halloran. I work with the ICT for Energy Efficiency team at Tyndall National Institute. I'm also a final year student of electronic engineering at Munster Technology University in Cork. So today I'm going to be talking about my final year project, which I'm working on in conjunction with MTU and Tyndall, and it's an automated battery lifetime calculation testbed for IoT devices. So just to give you a little bit of background and to just backtrack a small bit here. So what you see here on the left, this is a typical energy harvesting system that we would develop for an electronic load. So you could see here you have your harvesters which harvest ambient energies. You have some sort of conversion circuit, which is typically kind of like a DC to DC converter or something like that. Then you store it, so that would typically be in a supercap, and then that's all managed by a power management IC, which you can see at the top there. So in order to develop one of these systems, the most important thing is to first characterize the load that you're trying to design the system for. And that's what my project is all about. So what we typically do is we would characterize it using this instrument that you see here on the right, which is the N6705B DC power analyzer by Keysight. So that's just a little bit of background. So as I said, it's very important to characterize the load to develop these energy harvesting systems. And this is the current process that is used to do that. So step one would be to connect the device under test to the power analyzer and capture its current characteristics over time. So that would be stored in internally in the power analyzer. And then what we typically do is take a USB stick and extract the data that way. Then in step two, we'd pop the USB stick into PC. And in steps 3 and 4, we would graph the current profile for the device. And then using this current profile, we would go off and manually calculate the duty cycle, the average system current, and then based on those two specs and characteristics, for a selected battery, we can go off and estimate the battery lifetime based on those. So there's some issues with this process, and this is kind of the reason why this project's being developed. So the issues with this is it's very time consuming. So if you can imagine if you to do this 10 to 15 times a day, the power analyzer has an internal memory limit of 4 gigabytes, so that has to be wiped every now and again. And it's prone to human error as well. So as you can see, there's a lot of steps in here where human error can come into play, and the whole test has to be repeated if there is an error, and it's just not it's not very standardized. So the improved process, which is basically what my entire project is about, is to take out as much human error as possible. So the device under test would be connected directly to the power analyzer, and then the data is read via USB to the user's PC. And then that's all displayed neatly on an application which is being developed as part of the project as well. So I'll give a demo of this in a sec. This is just kind of give you an idea. So basically the improvements then is it's more repeatable, it's quicker, more accurate, more memory efficient, because the data is being read directly from the power analyzer into the PC. And it's automated and standardized then for different load devices. So if you wanted to test 10 different characterize 10 different load devices, you have the same process to do all those. So that's always good. So I'm just going to run a little demo. So I just put this in case anyone wants to go back and kind of figure out how it's working exactly, but I think it might be just more beneficial to run the demo of the application. So this is the application itself. So the first step, if you were to use this application, is to read in some data from a device that's been characterized. So for the purposes of this demonstration, I prepared an example data set. So I think Pete mentioned that the LoPi expansion board earlier. So this is literally just a data set for current consumed by a LoPi microcontroller over time. So the user goes off, imports the data. You can see it here in the raw data imported text box. So this is current consumed over time. The user can then plot that data to see what it looks like, and that's all great. And then kind of the important feature and the whole purpose of the application is you by pressing this calculate button, the back end of the application goes off and calculates these characteristics of the device. So the average sleep current, the average transmit current, the average system current, and then the duty cycle. So the next step then is if the engineer wanted to go off and say, well, I need to validate that because I'm not sure if that's exactly right. You know, you might have 100 transmissions in this data set that's imported. You can go off and you can trim it down, and he said that's great, and you can see even just by eye that is around 28%. The duty cycle is around 28%, and you can kind of validate those that way then. And like, you know, the application is titled Battery Lifetime Calculation Testbed. So another important factor is to actually be able to put in some battery characteristics and get an estimated battery lifetime. So the next step is the engineer can come along and put in the capacity of the battery they'd like to use. So if they wanted to use a 3.3 amp hour battery, pop that in here. So that's in milliamp hours there, and click calculate. And the application's backend will go off and estimate battery lifetime in hours and battery lifetime in days for this particular device as it's configured from this data set. So that's kind of the most important feature of it. But then one added feature that could be handy as well is if the engineer sees this estimated battery life and they can't go off and change the capacity of the battery that they have to use, they can say, right, instead of having to go off now and reprogram it and try to change the duty cycle and get the system current down, they can say, right, if I could get it down to 5%, what would be the improved battery life? So they can just pop that in here, and it recalculates and gives you a new battery life in hours and battery life in days. So that's the application, and that's where it is at the moment. Now, obviously, we're going to add a lot more kind of bells and whistles, which I'll get into in a sec, but that's the general operation of the application. So I'll just pop back to my presentation. So as you can see there, the program design, the application is launched, a data set's imported, the data is plotted, the device characteristics are calculated, the data view is trimmed so that the engineer can validate the data that's being used. The battery capacity is entered, and then the application goes off and calculates a battery life and displays it. And this can be done over and over and over. So what's actually under the hood? So this is kind of a busy slide, but I said I just throw it in just to give anyone who's interested in how it's actually doing all this stuff. So basically, the Power Analyzer has 3 different hardware interfacing options. So you've LAN, USB, GPIB, and then it has a number of instrument drivers that it can be used as well to interface in software with the instrument. So the main takeaway from this slide is just to know that it's the hardware interface is USB, and the drivers used are from the IVI Foundation, and they're specific to the N6705B DC Power Analyzer. And the language that the application is programmed in is C# and XAML. And if you don't understand that, it's not that important. So in the interfacing in action, so this is kind of the next step in the project. So as you saw there, I imported the data from a data set that was saved on my PC already. So that what we want to do is now be able to read the data in directly to the application. So this just demonstrates some of the work that's been done on that. So I'll play this little video and then I'll go through exactly what's happening. So as you can see, this is the Power Analyzer. It's reading 4.8, 4.7 milliamps. It's connected to channel 1. Oops, sorry again. Yeah, so you can see it's reading in the data. It's connected to channel 1. It's connected to an analog devices microcontroller eval board. It's also powering it. And then this is just some of the back-end stuff. So you can see here, channel 1 is selected in the back-end software. A measurement pointer is set up and a measurement driver. The sample interval is set to 10 milliseconds, and then it just goes around this loop here and just takes the reading that's coming in from the USB. So if I just run that, you can see, yeah, so you see it just reads out 4.7 milliamps to the console. Now, obviously, this will be reading into the application when it's complete, but you can see then it's 4.7 milliamps being read in on the Power Analyzer as well. So yeah, that's the interfacing in action. And then just a little bit about that use case. So as I said, what was being tested there was the ADXL Eval 362. So that's an accelerometer evaluation board by analog devices. The programmer specified to me that there would be a peak every 70 microseconds. So in my software in the back end, I set the sample interval to 1 microsecond. And this was the process that I kind of explained at the start that we were trying to do. So we're trying to get the device under test directly connected to the power analyzer and reading the data directly to the PC. And that was displayed on my console, and this was the result. So we could see that we captured a peak every kind of 70 microseconds. So the next step, I want to implement some more robust battery models with some drop-down options. So we're working on that at the moment. Connect the back-end interface into the front-end GUI. So as you saw there, when I was demonstrating, I read in the data set from a previously characterized CSV file for a different device. But I want to be able to read in the data directly to the application and display it in real time. And then package and test the application. So if anyone's interested, in a couple of months, we'll be looking for people to kind of test it and give feedback on it as well. So to summarize, the project is set up and it's aimed to automate and standardize this process you see here on the left. And we're working on that, and the application that we're developing at the moment is seen here on the right, and it's more automated and standardized. So thank you very much, and I suppose you'll give questions at the end. So I'll just hand back to Peter now, and any questions at the end, just let me know. You there, Pete?
Yep. Okay. Let me just. I should better be sure now. Like this. Okay. There we go. Okay, so just to finish off, just a couple of slides to talk about the virtual access offering and other simulation work in enables. So just wanted to mention that the colleagues on enables in Southampton University and University of Perugia in the NIPS lab, that's a noise and physical systems laboratory. They've created these open source libraries of ambient energy sources. So these are like vibration signatures, wind levels, radiance levels. Now, as you can see there, there's things like, you know, vibration around engines and all this sort of stuff. So this is an open source database that's available to all when you sign up to Enables, and it enables researchers to evaluate designs and analysis from a common data set. So you can have a better comparison between different areas of the performance of harvesters. So that's really useful, and that's a very extensive database. And then some of the other offerings from Perugia is these data acquisition kits that can be used to acquire more data and to further update the database. And so, you know, there's this kit available, and again, that this is simple enough to be able to get access to. And then lastly, there are also other simulation tools. Okay, so our colleagues in Perugia and Southampton have also have simulation tools that are simulating, in some cases, down at, you know, the harvester level and this type of stuff. So again, so some links there, and if you go to the Enables website, you better get all the details and that sort of stuff. And so yeah, so just to finish off, come and join our ecosystem. It's free of charge. You can get access to expertise and laboratories from the Transnational Access Program. There's joint research activities that are, you know, doing a lot of good work, and there's a number of publications that you can get access to. So all you need to do is sign up. And the work is followed by these following projects, and that's the end of our presentation.
Thanks very much, Peter. Thanks very much, Ross, as well. So what I think we can do now is go into the questions and answer session. So first of all, if you can, we have received a couple of questions when people registered for the webinar. So if it's okay with everybody, let's start with those. So the first one was, can we use these tools to simulate energy patterns, energy obtained from an energy harvester? So I'll put it to both you, Peter and Ross.
Yeah, so I think I can partly answer that question in that, as I mentioned earlier, even though in the tool there are pre-characterized PV cells and TEGs, there is the facility for the user to be able to do their own characterization. They can store that in a specific format in one of the directories, and the software picks it up and it becomes part of the pull down menu, so that you can select that in that way. In terms of the characteristic of the energy, if you like, at the moment it's sort of hardwired in there that there is a certain amount of time every day that the lights are on and they're off, and the heat source is a constant heat source. Yeah, there's no sort of time variation on that, and these are things that we're thinking about that we might do in future versions.
Very good, thanks, Peter. The second question we had is, which protocol is the most recommended for energy harvesting solutions? So again, I'll put it to both the two of you, whatever one you want to reply, please.
Yeah, so that's a common question, and it really, like, it depends, you know. So there are a lot of protocols, but it depends on your specific requirements, you know. And there really isn't a one case fits all. So, you know, it ranges from LoRa, which can be configured to be lower power, but is not the lowest power. But if you need long range, then that might be the best solution for you. If you have a very short range and all you want to do is just send data without any sort of acknowledgement or recognition that the data got to the endpoint, like in a broadcast way, and you only want to go a few meters or so, then BLE might be the right thing. Then you've got various flavors of mesh type networks. So Zigbee might be an example of that. But again, really that depends on, you know, how much data you're trying to send, how often, what sort of range, what the sort of latency is, whether you sort of, you know, need to work in real time or not. So there's a lot of other factors in the selection of the protocol, as well as the power, and depending on how you set all those networks up, it will change the power characteristics of it.
Very good. Yeah, thanks very much. So I open it now to on the floor. Does anyone have any questions for either Peter or Ross? So if you could turn on your camera and your microphone, please, and ask your question.
Hello.
Hello.
Can you hear me?
Yeah, we can. Yeah.
Should I turn on my camera? Hello?
Yeah, go ahead, please.
Yeah, actually, thanks for a wonderful session by Mr. Peter and Mr. Rose. Actually, I have a question for Mr. Peter. Actually, this simulation tool, whatever he has told, is it applicable only for hardware models, or in case of any, in case if I would like to develop any software, because I saw only hardware models are being shown there. In case if I have to simulate any of the software, maybe I make some, I try to make some changes in the software by implementing some what do I call, sleep modes and all. Can that also be simulated?
Not as the tool is currently
Okay.
designed, yeah. So like it's something that could be incorporated later on, and we do have sort of other sort of internal bits of simulation, shall we say, or software developed. But yeah, no, in terms of that tool, that is a sort of a straightforward characterization of pieces of hardware, and you enables you to experiment with different combinations and different characteristics. But yeah.
So right now it's applicable only for hardware, right?
Yes.
We can simulate for any kind of hardware models.
Yes.
Okay. Thank you. Thanks a lot.
Thanks, Peter. Is there any other questions? Okay. Listen. Even if you don't think about something now, you get a question in the next few days or whatever, just send it to me, the same email address that you got when you registered, and I'll pass it to both Peter and Ross, and we can reply to your questions offline. One thing I want to mention before we close the session is there'll be another Enables webinar at the end of next month. So on the 31st of March, we'll be looking at energy harvesting solutions in real world cases. So again, if you follow us on our website or so on, or we'll send you a follow-up email, we'll give you details on the time and how to register and so on. And finally, as usual with Enables, as I said, you can find updates and news on our own the website. You can follow us on Twitter or on LinkedIn, and you can also have a few videos showing the different technologies and things available through Enables. So through all those, please follow us, and you'll know what is happening and what things are we organizing and what you can access. Any other final questions or comments? Okay, so we'll leave it. I thank you again for taking part. Thanks again to Peter and Ross for very interesting talks. And I hope you found them interesting, and we'll be in touch. Take care.
Thank you.
Bye-bye.
Thank you.
Thanks, guys.
Bye.
Well done. Nice. Bye.
Thanks. Bye-bye.